Hello, and welcome my colleague Katrina. My name is Ketan, and we'll talk about how you can make data quality an intrinsic part of your machine learning and data product development strategy. I don't have to convince you, you probably already know about this, that machine learning models are only as good as the data that is fed to them. Let me illustrate this with an example. Let's say we wanted to train a model that would predict whether a given image of a food item was a hot dog or not. Then in this case, the input data set would contain a bunch of labeled images where you would have classified every image as being a hot dog or not. What if there were lots of images that were misclassified? Many of them were labeled incorrectly as being hot dogs when actually they were pizzas. The end result would be that we might end up classifying a pizza as a hot dog. Is that an expected value? And how do you solve this problem? You always ensure good data, right? Easier said than done. Another option is you periodically assert the data quality of your data set. Let's say you are getting a streaming data set or you're continuously getting the data from somewhere. You run an assertion every few minutes, every few hours, every few days, whatever it is. Another option is you assert the quality of the data set after it was created. So every time you get a few data set, you run some transformations and you assert the quality. But I always have a question on this. What if you want to transform the data on the fly? What if you access the data between assertions? And what if the assertion fails? How do you recover from the bad data? You got some data, you kept it, in the raw form, and now you're converting it and you're now asserting the value. How do you recover? Which is very often the way data is used in machine learning. So at this point, I think I want to make a assertion, a real assertion, and I think data quality should be an intrinsic to the process and not an afterthought. To illustrate this, the remainder of the talk will use an example. It will be the California housing example. We are all aware of housing is very important, and the prices of houses are always on the top of our mind sometimes. So this example is very interesting because it contains very understandable data. It's a small data set, easy to explain, and it also has a lot of different data types as an input. For example, the input features can be things like latitude, longitude, average bedrooms, age of the house, and so on. And the prediction or the regression variable here is the median house value. When you look at this data set, this is how usually the data set is. It's not obvious that a latitude has to be between negative 90 and positive 90 degrees only. Is minus 91 an acceptable value? It's not obvious. Similarly, it's not obvious if average rooms can be a negative value, or is 105 average rooms an acceptable number? And this is a common problem in most of the data sets. They do not carry this contextual constrained information. But before we get to the solution of how this could be solved, I think there is a bigger problem here. Production machine learning has a complexity problem. What I mean by that, to make models that are production ready and to deploy them consistently, there is a large number of tools that as engineers and researchers we have to use today. And this image is from a popular paper that I think everybody's seen and probably frankly quite bored looking at this image. But I want to use this image to drive one point. The number of tools is large. And I don't think I can be certain that all of these components are compatible within a stack. So it's a very hard problem. How do we solve it? Whenever I'm faced with a very hard and strong, hairy problem, I like to go to the first principles. So what are the first principles? What do we know about the problem or about where we are good at? So we've learned over the last few years that, or maybe decades, that we can really build complex software. We can build complex software that can solve really incredible things today. And how does that work? It starts with the smallest fundamental building block, and that's a function. A function is essentially a program that takes inputs and produces some outputs. And you can actually chain together multiple of these small functions together to form a much more complex organism, which is software. In machine learning, the inputs can be features and labels. The program can be the learning algorithm itself. The output is the model. Now, I actually think the model itself will become a program at the next step where given features, it produces predictions. And also, if you think about how the features came about, they came about from raw data. So you took raw data, you applied some transforms, and now they're features. So this itself is a very complex system of multiple functions working in sync to produce an effect, and that is given data, you can produce predictions. And one thing that we learn from here is that every program has inputs and outputs, and what we call them as strongly typed interfaces. And I think strongly typed interfaces are very important because they enable static analysis, they help in reduce errors, and so on. This is why more and more languages are becoming type safe, and type safe languages are really popular. But in the data and ML world, this is not that common. I want to argue that making type safety as a first class citizen within machine learning and data can improve auditability. It will be so much easier to debug a pipeline when it fails. I can easily pinpoint errors and also maybe reproduce the errors by rerunning the same set of inputs parameters to a specific function. Also, breaking down into multiple functions and putting them together would help in improving understanding the lineage of how did a prediction come about, where did the model come from, what were the features that were put in, and what was the raw data that led to the predictions. Similarly, I think using static type safety can help in reliability because you can reduce the runtime errors, it can improve readability. That's one of the best parts of types and type safe languages. They are self-documenting. The name of the function, the name of the variables, and the type helps you understand, get a lot of context. It also helps in reproducibility because you can reproduce results and errors. I also think it helps in efficiency. For example, let's say if you can memorize any function's execution based on the input values it received, assuming that it has no side effects, then you can reuse those materialized values anytime the same function is invoked with the same parameters. Also, the data dependencies can help uncover parallelization opportunities. Now that we discovered how type safety can improve your machine learning and data products, let's learn from Katrina how open source software like Flyte and Pandera can be used to solve problems in real world.
Thanks, Ketan. I'm Katrina, and let me start by talking about Flyte. Flyte is a data and machine learning aware orchestration tool built with these type safety and data type principles throughout. As an overview, Flyte lets you define pipelines or workflows, which are a collection of tasks used to train and evaluate your machine learning models. With our housing prediction example, we can define a few types such as dataset, which is pandas data frame with the schema defined here, a few intermediate splits and training result types, as well as a set of hyperparameters that we use for model tuning. At the core, tasks are atomic units of work with strongly typed interfaces and are containerized for reproducibility. Workflows model the data flow between tasks. In this case, we have a get dataset stage, which fetches our data, yields it to our train model stage, which then produces data which is used to evaluate our model and also summarize our training data set. This allows us to do things like generate strongly typed launch forms so that we can check types at execution time. We also use Docker when we ship tasks and yield them to the Flyte platform, which guarantees reproducibility as long as the tasks don't have any side effects. Flyte uses types throughout to statically analyze your data in order to catch any type errors before execution time, so you don't have to waste valuable training time. Because tasks are defined as simple Python functions, you can always run them locally and catch any simple errors before you start running your workflows on Flyte. However, if you do have execution type errors, it's easy to debug those using Flyte's rich outputs. And to further improve runtime performance, Flyte allows you to cache the outputs of a task. We use the type signature, and as long as you reuse the same inputs, we'll always store the outputs of a task, so you don't have to recompute them each time you run a task with the same set of inputs again. Even if you don't necessarily utilize task caching, Flyte can recover workflows for you automatically in the case of system or transient errors by fetching the previous results of a run and using them to relaunch or recover your executions. Because workflows are data aware, they come in with native task parallelism. As soon as the inputs for a task are materialized, you can immediately go ahead and run those in parallel rather than running each one individually in sequence. This comes with all sorts of performance improvements and also allows us to trace model artifacts as they're transformed throughout your workflow pipeline to understand data lineage and how these data artifacts are produced. In this case, you can see here how the inputs of a downstream task reproduce as outputs of an upstream task. But making assertions about types isn't necessarily always enough. Values matter too. In this case, for the housing price prediction example, we know things like square footage can never be negative, and it doesn't make sense to allow those in our data pipeline. This is where we introduce Pandera, which is a statistical typing and data testing library for data frames and your data collections. Pandera allows you to do cool things like define constraints on individual values in your dataset. This includes things like no negative square footage or more complicated examples that you can accomplish using regex string matching. Pandera also allows you to make statistical constraints on the entirety of your data collection. This means you can do things like define means or expected standard deviations or other statistical distributions you expect to see in your data at runtime. Pandera is really easy to use. All you have to do is define your schema and then a check types function, which is called at runtime, in order to validate your data at any point where it's used. Pandera and Flyte naturally play well together. You can define a Pandera schema and use that data type throughout your Flyte tasks to guarantee that all your type assertions will be utilized throughout your Flyte workflow. Revisiting our housing price example, in this case, we assign a Pandera a constraint to the median house value that we expect. In this case, we use that to make assertions about the mean. We can see here how we use Pandera in order to make assertions about the mean value for our median house prices. Pandera lets you do cool things like immediately figure out when your data has missing columns, or when your data has the wrong type, or even when your data is using the wrong values. Pandera also again operates on collection at large, so we can see here we raise issues with the wrong statistical distribution. And so revisiting kind of our first principles approach that Ketan went over before, you can see how we can use Pandera and Flyte in order to make assertions about the input and output types flowing throughout our workflows. We can do things like assume type safety, we can constrain the values of our inputs, and because all of this is tracked throughout, it gives us guarantees about reliability and data trustworthiness, which means that ultimately our models can be reproducible as well too. And that's it. There's 3 takeaways from this Flyte. The first is that Flyte is an open source machine learning orchestration platform that has deep integration with type safety throughout. 2, with Pandera, you can ensure the quality of your data flowing throughout your pipelines and make assertions about the correctness of those data and those pipelines by expressing statistical types within your code. And finally, when you combine Flyte and Pandera, you can build, deploy, and scale your machine learning pipelines, along with all the benefits of type safety guarantees that allow you to immediately identify errors at runtime and help you fix them. If you're interested in learning more, we invite you to check out the official docs or come find us on GitHub. Thank you so much.